Exponential functions are used to model many natural phenomena, including population growth and interest accrued in savings accounts. In this section, we'll review the graphs of exponential functions, solve exponential functions, and model real-world situations with exponential functions. Grab your notes because Precalculus Online starts right now. In section 5.3, we look at exponential functions. And this section starts off with the quick review. So go ahead and review these laws of exponents and then try to work the 5 problems here. Pause the video and then pick up the video again to check your work. So go ahead and pause that now and work these 5 problems. Alright, so you should have had some time to do these problems. Let's take a look at the answers. Number 1, x to the 7th times x to the 5th. Notice that you have the bases are the same and you're multiplying with exponents. So when the bases are the same and you're multiplying, the key here is to add the exponents. So this becomes x to the 7 plus 5 power, which is x to the 12th. Number 2, we have x to the 4th to the 9th. Here you only have one base, and that's what makes this problem different from the problem in number 1. And so the key here is to multiply the exponents. So we get x to the 4 times 9 as a power, and that's x to the 36th power. Number 3, we have xy, that quantity raised to the 4th power. So we give the 4th power to both the x and the y, not just to the y alone. Number 4, we have x to the negative 8 power. So really what we could do here is just simplify this by moving the x to the power into the denominator. When you shift an algebraic term from the top of the fraction to the bottom of the fraction, or vice versa, you negate the exponent. So if the exponent here is negative, when it goes down to the bottom, that exponent becomes positive. And vice versa, if it were negative exponent in the denominator, when you shift it to the numerator, it becomes positive. Number 5, we need to give the power of 3 to the 2 and to the x on the top, and we need to give it to the y to the 5th on the bottom. So 2 cubed is 8, x cubed over y to the 15th. So I hope that was a great refresher for exponents. And let's move on to graphing exponential functions. Example 1, create a table of values and then graph the function using the points from the table. The function is f of x is equal to 2 to the x. So I think I'll start my table here at x equals 1. If I have 2 to the first, then that's just 2. Because anything raised to the first power is just the number itself. So 2 to the first is 2. Then we have 2 squared is 4, and 2 cubed is 8. Then if I have a positive number like 2 raised to the 0 power, that is going to be 1. And now let's look at the negatives. So if I have 2 to the negative 1 power, 2 to the negative 1 power from the review that we just did, means that the base of a 2 is going to be moved to the denominator, and then you change the sign of the exponent. The exponent was negative, it now becomes positive. So this is 1 over 2 to the first, which is just 1/2. Similarly, if I have 2 to the negative 2 power, that's the same thing as 1 over 2 squared, which is 1 over 4. And also 2 to the negative 3 power is 1 over 8. So a couple of things to notice here. Notice that even if I use a negative exponent, 2 raised to that negative exponent is still a positive number. And in fact, there's no way to get a negative number by raising 2 to any power. There's also no way to get 0. So every time you raise 2 to a power, you get some positive number. Let's see what this looks like graphically. So if I plot, let's start with 0, 1. That was this point here. And then 1, 2, 2, 4, and 3, 8. And those are easy to plot. These, not so much. Negative 1 and 1/2, maybe right there. Negative 2 and 1/4, and negative 3 and 1/8, something like that. And as you move further to the left, these values get closer and closer to the x-axis. So we're just going to draw it right here like this, and then sweep it up through these points here. As we move further and further to the right, the values increase without bound. So let's make a few notes here. So 2 to the x is always positive. What we do notice here is that we have a horizontal asymptote. An asymptote is just a line that provides a guide for where a function is headed. And in particular, this horizontal asymptote is y equals 0. A lot of times we draw it as a dashed line here, and you could draw it all the way across, but really we only need it on the left side here. So I'll just stop there. Number 2, 2 to the x is defined for all values of x. So that means the domain is going to be negative infinity to infinity. This particular function, 2 to the x, is called the doubling function. And that's because every time you move over 1 unit on the x-axis, the y value gets doubled. And you can see that from here, from 1 to 2, and then 2 to 4, and then 4 to 8. What's not as obvious is that you could do it with decimals as well. So for example, suppose I look at this, let's call this is the f of x function. So let's say we have f of 1.7. I'm going to plot that. Now I don't know what the value of that is, and I don't need to know what that value is really. You can plug that into your calculator if you'd like, but for this purpose we don't need it. Then if I find the f value 1 unit before that at x equals 0.7, it would be right here. Then what is the ratio of those values themselves? Well, it turns out that this would be 2 to the 1.7 divided by 2 to the 0.7. And one of our rules for exponents was that we could subtract these. And we get 2 to the 1.7 minus 0.7. But 1.7 minus 0.7 is just 1. So this is 2 to the first, which is 2. Well, that tells me that the ratio of f of 1.7 over f of 0.7 is 2. In other words, the function value is doubled. So if we have this height here, then this height is twice of those. So this doubled right here. Let's take a look at the properties of exponential functions. Now this one, we start with f of x is equal to a to the x with the a greater than 1. So first off, the domain is negative infinity to infinity. The range is 0 to infinity. And notice that I use the open parenthesis on the left side. That indicates that the range values are going to approach 0 and get closer and closer to 0, but never actually equal 0. Number 2, x-intercepts. Well, since the y's are never equal to 0, there are no x-intercepts. So we say none. The y-intercept was 1. The horizontal asymptote was y equals 0. And we can even put in a little note here that this one is as x approaches negative infinity. So you can have a horizontal asymptote that is on both sides, the left and the right of a graph, but you don't have to. You can have it only on one side. And when you have it on one side, you can specify which side it's on. For f of x equal to a to the x with a greater than 1, this function is increasing. And it is 1 to 1. The graph contains these 3 points. So negative 1 and 1 over a, so the reciprocal of the base, 0, 1, and 1, a. Number 6, the graph of f is smooth and continuous. Smooth means that it doesn't have any abrupt, sharp corners, no kinks in it. And continuous means that you can draw it without lifting up your pencil. So your basic exponential function with a greater than 1 looks something like this. Let's see some examples. Example number 2. Sketch the graph of f of x is equal to 4 to the x. Label the 3 points. And we'll also do the domain, range, and horizontal asymptote. So first off, recognize that it's an exponential and that the base is 4, which is greater than 1. That tells me it's going to be the increasing function, the increasing exponential. So it's going to look something like this. Here we're going to have the point 0, 1. Here we'll have the point 1, 4. And then the other point on this side is at negative 1 and the reciprocal of the base, 1/4. The domain is all real numbers, negative infinity to infinity. The range is 0 to infinity. And the horizontal asymptote is y equals 0. Make sure you include the y equals part because we are describing a line, and a line has to include which variable it's being represented by. Example 3, sketch the graph of g of x is equal to 3 to the x minus 2 plus 1. Label the 3 points, and of course we'll do domain, range, and horizontal asymptote. Well, this time we have some transformations. So recall transformations from college algebra. And what we need to do is identify what the parent function is, or the base function. In this case, it's y equals 3 to the x. And then identify the transformations. So x minus 2 in the exponent means that the function has been shifted 2 to the right. And the plus 1 on the outside means that the function will be shifted 1 up. Now, one thing that you can think about is turning this into sort of how you change the points. Since you're going 2 to the right, you add 2, and you're going 1 up, you add 1 to any of the base points that you have from your parent function. Let me graph the parent function quickly. It's the increasing exponential, and it goes through 0, 1, 1, 3, and negative 1, 1/3. And now we take these points and we shift it using the transformations. So the new graph, and this is the graph of G, I'm going to start with 0, 1. So 0, 1, and if I add 2, 1 to that, I end up with 2, 2. So the point 2, 2 is a point on the graph. If I go to the last point here, 1, 3, and I add 2, 1 to it, I end up with 3, 4. So 3, and there's 4. That point there. Now this one, I avoided this one because it has a fraction, but it'll be okay. If I take the point -1, 1/3, and I add 2, 1 to it, I end up with 1 4/3. 1 4/3 would be about right there. In addition to the points on the graph being shifted through the transformation, the horizontal asymptote is also shifted. And it's shifted by the vertical component. So the vertical shift was add 1. So since the original horizontal asymptote was y equals 0, the new horizontal asymptote is y equals 1. And now let's draw the graph. Let's describe the domain. The domain is still all real numbers. The range has been shifted. The range is now 1 to infinity, open at 1. We can get close and closer to 1, but we can never reach 1. The horizontal asymptote is y equals 1. That was the increasing exponential function. Let's look at the decreasing exponential function. Notice that the characteristic is that the base, a, has to lie between 0 and 1. So the domain is still negative infinity to infinity. The range is still 0 to infinity. The x-intercept, none. The y-intercept, still 1. The horizontal asymptote, still y equals 0. And then here's where we get the change. F of x equal to a to the x for a between 0 and 1 is the decreasing exponential. It's still 1 to 1. The graph still contains those 3 points, -1, comma, 1 over a, 0, 1, and 1, a. And the graph of f is still smooth and continuous. So the other thing that's changed here is the fact that it's decreasing. Let's draw a little example graph here. So it looks something like this. And the way that you're going to compute these 3 points is a little bit strange. So let's take a look. Sketch the graph of h of x, which is equal to 1/2 raised to the x power. So we have the decreasing graph. So let's compute 0, 1 is one of the points on the graph. 1, a is another point. Well, now the a is a half, so it's between 0 and 1. So it goes right there. And then for -1, we take the reciprocal of the base. Well, the reciprocal of the base is the reciprocal of a half. When you take the reciprocal of a fraction, you end up just flipping the fraction over. So the reciprocal of a half is actually 2. And so that puts it up here. So that's a little bit strange, but that's okay. Everything else is the same. Draw the graph. Denote the horizontal asymptote. The asymptote this time is on the right side. The domain is all real numbers. The range is 0 to infinity. The horizontal asymptote is still y equals 0. Let's look at example 5. Sketch the graph of k of x is equal to negative 2/3 raised to the x plus 2 power. We have some transformations again. So our transformations are, the negative in front is a reflection over the x-axis. And we have plus 2 in the exponent, so that's going to move it 2 to the left as a horizontal shift. The parent function is going to be y equals 2/3 to the x. Let's go ahead and sketch the parent function. Since 2/3 lies between 0 and 1, we know it's the decreasing exponential. The parent function goes through 0, 1, 1 comma 2/3, and negative 1 comma 3/2. Let's do the transformation in stages. The first transformation I'm going to make is the reflection over the x-axis. A reflection over the x-axis negates the y-coordinate. So we're going to flip it over the x-axis. So this becomes 0 comma negative 1, 1 comma negative 2/3, negative 1 comma negative 3/2. Now let's shift it 2 to the left. Shifting 2 to the left only changes the x values. It does not change the y values. So 1, 2, 3 to the left here. So 1 comma negative 2/3 shifts back 2 to where it is negative 1 comma negative 2/3. 0 negative 1 shifts to negative 2 comma negative 1. And negative 1 comma negative 3/2 shifts to negative 3 comma negative 3/2. The domain is still all real values. The range now goes from negative infinity up to 0, open at 0. And the horizontal asymptote is still y equals 0. Next, we have an exploration for you to perform in your TI-84. So go ahead and take out your TI-84. Enter this function, 1 plus 1 over x raised to the x power. And the goal is to determine what happens to this function as the x goes to infinity. So let's go ahead and think about this for a second. Because we have an x in the exponent, and we're going to see what happens as the x values get larger and larger and larger, you might think that the value of the function just explodes and just goes to infinity. But on the other hand, we have this 1 over x on the inside that's being added to 1. So as x gets larger and larger and goes towards infinity, what happens to the value of 1 plus 1 over x? Well, as x goes to infinity, 1 over x goes to 0, so 1 plus 1 over x approaches 1. And 1 raised to a power is still 1. So the question is, who wins? Is it going to blow up and go to infinity? Is it going to approach 1? Or is there something sort of in the middle that it's going to settle on? That's what you need to figure out here. So go ahead, follow these directions, pause the video, and then once you have it all set up, work through the problems, answer the question that's below, and see if you can come up with the answer. Then unpause the video to see the results. All right, so hopefully you had a chance to do the exploration and you come up with these numbers or something thereabout. The decimals were pretty important because, as you can see, it's sort of settling in on a value. That's about 2.718. So the question is, as x approaches infinity, what value does f of x approach? And the answer to this is e. E is the letter that we've given to denote this special value that is defined by that exact equation that you worked with. Its decimal value is approximately this, 2.718828282459. It's not rational, so it doesn't have a repeating decimal, even though it does sort of get on a little roll here with the 1/8 and the 2/8. And some people call this the natural base. The natural base. And this is the number that sort of controls growth rates in nature and is very easy to work with in precalculus and calculus and so forth. Let's take a look at example 6, and it says graph. I didn't want to tell you what to graph because I didn't want to give away the answer, but what you're graphing here is y equals e to the x. So e is approximately 2.7. That makes e bigger than 1, so this is the exponential function. It'll look something like this. Okay. What you'll want to note is that there are two different buttons for e in your calculator. One of the buttons is e to the x, and it is there because we use e as the base of an exponential function so often that the makers of the calculator decided to give it its own button. There is also a standalone e, but we very rarely need to use it. Let's turn our attention now to solving exponential equations. We have this sort of golden rule for solving exponential equations. It says if a to the u is equal to a to the v, then the u and the v must be the same. This is just a restatement of the fact that the function that is a to the x, the exponential function, is a one-to-one function, where this is the evaluation at one x value, this is the evaluation at the second one, and since exponentials are one-to-one, then the only way that they could have the same y value is if they started with the same x value. In general, the rule that we follow is this. Make the bases the same. Then set the exponents equal to each other. And that's how we solve exponentials. So let's look at example 7. Solve for x. 3 to the 2x plus 5 is equal to 9 to the 7 minus x power. You look at the bases. We have a 3 and a 9. And they're not the same base. So we need to do something to make the bases the same. Notice that 3 and 9 are in the same base family. That base family is the 3 family. So we take 3 to the 2x plus 5, and that side is fine. The 9, however, we need to do some manipulating. So I need this to be a base of 3, and then the question is 9 is what power of 3? Notice you have to use powers. You can't use multiply or add or anything like that. It has to be powers in this case. So 9 is 3 squared. So the right side becomes 3 squared, all of that raised to the 7 minus x power. The left side stays the same, and I simplify the right side. We have base, exponent, exponent, so we multiply the two exponents. Now that the bases are the same, we can set the exponents equal to each other. And solve for x. So we have 2x plus 5 is equal to 14 minus 2x. Moving the x's to the left, I get 4x. Moving the numbers to the right, I get 9. And so x is equal to 9/4. Example 8, solve for t. 4 to the t is equal to 1/2 raised to the t plus 1. So again, we have exponents. The variable is in the exponent. We want to use some rule like this. We look at the bases. They're not the same, but they both belong to the 2 family. So 4 is 2 squared. Raise that to the t. 1/2 is 2 to the negative 1 power. Raise that to the t plus 1. Notice that whenever you need to invoke a reciprocal in order to get these to work, you use a negative exponent. Simplify the exponents. On the left, we get 2 raised to the 2t power. On the right, we get 2 raised to the negative t minus 1 power. Now the bases are the same. Set the exponents equal to each other. We get 2t is equal to negative t minus 1. That gives us 3t is equal to negative 1. And so t is equal to negative 1/3.